So it's really delighted to be back here. So my family and I spent calendar year 2013 living in Santiago, and I actually had a root card and all of that, so I really lived here. And my children attended school here, and I got to commute here by car every day, which was whatever. And I had a great year. And actually, this research project started while I was here. So we recently submitted a paper for publication. And this is work with, so Paul Grigas, so this is me. Paul Grigas was a PhD student at MIT, who's now on the faculty at Berkeley. And his doctoral student right now is Alfonso Lobos, who was a master's student here. Okay. And then Rahul Mazumdar has also participated in this project. He's a statistician at MIT. And this is, I don't know why this is getting cut off, but Pontificia Universidad Católica. So let's see, I have a little less than an hour to speak with you about this topic, and I think what I'm going to do is try and engage you in it. That is, I'd rather not just be giving you slide after slide after slide and have you not understand anything. So my sense is I won't get through all 85 slides. I might get through about 20 or something, or maybe 30. So, but please ask me questions. I mean, I mean that sincerely. Let's see if we can have something sort of real here, okay? Oh, whoops. Okay, so we have a paper on this, and this is, I say here we have another paper, which I call a cousin paper, because this is all part of a thrust that Paul Grigas and myself and Rahul Mazumdar have been doing to try and strongly connect what's going on in modern statistics and big data with the field of optimization. And so this is quite of a part of a fairly broad agenda to see how optimization can inform 21st century statistics. Okay? And so here's an outline. I think maybe I'm not going to get to this stuff at all. And I'm probably only going to get about halfway down this page, is my guess. But I want to first talk about optimization methods for what's called convex optimization. And then I want to talk about logistic regression and two different ways of thinking about logistic regression. The statistician's way of thinking about it and a machine learning way of thinking about it. And I'm just going to ask, like, who here knows anything about machine learning? What? No one really. Okay. All right. That's okay. Okay. All right. Okay. And is this Pim? Good to see you. All right. Wow. Thank you so much. And your great intellect. Okay. All right. So let me teach you a little bit about some algorithms, actually. I'm going to review three very, very useful algorithms called, oops, I'm going to get this right here. Greedy coordinate descent, gradient descent, and stochastic gradient descent. Okay? And so here's what I have to say about them. Greedy coordinate descent is really the philosophy of let's go in the best coordinate direction to optimize a function. And there's also gradient descent, which I say here is go in the direction of the negative of the gradient. People are most familiar with that. And stochastic gradient descent, go in the direction of the negative of some estimate of the gradient. Okay, and all three are going to be very important. All right. So what is our problem of interest? Our problem of interest at the moment is just to minimize some function, okay, over all of x. And x is a p-dimensional vector. Okay. And I want you to start to get used to, since we're in the big data era, okay, that p is a very large number. So the number of components of p maybe is 1 million. Okay. So my function is differentiable and convex, and convex just means if I take a convex combination of these points here, f is less than or equal to the convex combination of the resulting objective function values. Okay? And we're going to say, I'll use this notation, norm of x denotes a given norm, and I'm just going to show you some quick things about norms, and if you're not following what I have to say about norms, don't worry about it. Okay? So there's different kinds of norms. The norm that most people are used to work with is what's called the L2 norm or the Euclidean norm, and that's just, say, the square root of the sum of the squared values of the components of a vector. And it has what's called the dual norm, which I put a star here for. But the dual norm is the same thing as the norm itself. If my norm is what's called the L1 norm, is just the sum of the absolute values, it has a dual norm, which is what's called the infinity norm. And what is the infinity norm? That's just the largest of the absolute values of the components. Okay? And its dual norm is the 1 norm. And if you don't know anything about norm duality, don't worry. Okay? All right? So here's my optimization problem again. All right? And then we say that the function has a Lipschitz gradient with some parameter L sub f. If basically this statement sort of says changes in the gradient can be bounded nicely by changes in the variables itself. Okay, that's all. All right, and just because of the way duality works, we measure the gradient in the dual norm of the original norm. Jorge Vera knows exactly what I'm talking about here. Okay, and maybe not too many others. I'm not sure. Okay, huh? Some? Okay, good. All right, all right. And then I can define a norm on a matrix. Let M be a linear operator, a matrix, say from p-dimensional space to n-dimensional space, and I can define a norm on the matrix. I'm not going to bother with that. Okay, but this will come up, but I just want you to think these things just happen. So here's greedy coordinate descent. The greedy coordinate descent method is just sort of says, wherever I am in an algorithm, if this is my current point, I compute the gradient, and I then see which component has the largest magnitude, where the gradient has the largest magnitude. So I compute the gradient. I find the index of the component with the largest magnitude. Okay. I set my direction then that I'm going to go to be, this is sort of the unit vector in the jkth component, okay, times the sign of this. That just makes sure I'm going in the right way. So if the partial derivative there is positive, I'm going to go this way. If the partial derivative is negative, I'm going to go the other way. So that's my direction. I choose a step size, and then I take my step. Okay, that's greedy coordinate descent. Okay, this algorithm was really probably developed in the 1940s or 1950s. No one cared about it until very recently. Okay, and now there's just been a lot of results on it, and I will show you some. We're going to get to that. Okay, so there's a bunch of different ways we can choose the step sizes, for sure. Okay, all right, I'm not even going to talk about that. But here it is. It's sort of if here's my current point, and say then my gradient is going to be pointing. You can think the negative of the gradient is just going to be perpendicular to the contours of the objective function, which would be here. And so the largest component magnitude-wise is going to be the first direction, and the negative of my direction would be going this way. Okay? And so I want to show you the power of modern optimization, what's been going on the last 10 or 20 years. So watch this. If I assume my function is convex and the gradient has this Lipschitz constant that I mentioned earlier, okay, then I'm going to show you a pretty powerful result. It's not due to me. I wish it was, but it's not. But whatever. It's kind of nice. All right. So I'm going to be interested in two sets. One is going to be the set of all points whose function value is at most that of the starting point. So, And this is what's called the level set of the initial point. Okay? And then the other is the set of optimum for this problem. Okay? And I'm going to define this quantity, dist sub 0, to be basically among all points that are in the initial level set. Okay? What's the largest, shortest distance to the optimum, to the set of optima? So the set of optimal solutions is here. Here is the level set of the initial point, which was here. And so maybe this point here, its closest distance to S star is going to be this. And so that's going to be, we're going to call that the distance. So you can think of, it's the worst distance, it's sort of the worst distance from the optimum. Okay? All right. So here's a result. Maybe due to Amir Beck and Tetrashvali, maybe Yuri Nesterov, whatever. Okay, so watch this. So to Sergio's point, okay, if I set my step sizes at each iteration to be the infinity norm of the gradient at that iteration divided by that Lipschitz constant, then for each k, the following inequality holds. This says the optimality gap is going to be at most 2 times the Lipschitz constant times that distance thing squared divided by k plus this guy. And of course, this guy is going to be a positive thing, so I can just sort of say it's strictly less than this. Okay? And if I just look at this thing here on the right, all right, that's a fairly powerful statement. It's not as powerful as one would love. Like, this is not linear convergence. This is not quadratic convergence. Okay? But this sort of says, you know, basically the more iterations, the smaller this gap becomes, the smaller this number becomes, right? And then this number k hat naught, here's its definition. It's whatever, whatever, whatever. But I want you to look at the denominator here. This says if the initial point is in fact has a very good objective function value, this denominator is going to be tiny, which means k hat naught is going to be big, which means I get sort of, this is the initial kick that I get from having a good starting point. Okay? All right. And as it turns out, you might sort of think, well, maybe someone could prove this kind of a bound cannot be improved. Okay? So in other words, you can come up with generic examples where this bound cannot be improved. All right? So that's one result. All right? It turns out other things can be bounded as well. So I'm not going to bother with this up here, but again, if I set my step sizes this way, I can also show that during my algorithm, in fact, at least one of my gradients is getting small. So that is the norm of the gradient of one of my iterates up to k is decreasing at the rate basically square root of k. All right? That's another thing you can prove. And we can go even more. I could also say, again, if I set my step sizes here, I just changed slides on you. Sorry, hold on. Yeah. Right. So this was the bound on the gradients. Now I'm going to go to the next slide. And then it also says, in fact, for each k, its distance from the initial point is going to grow only at the rate square root of k. So that, and you might sort of think, well, who cares about this? Statisticians are going to care very deeply about this because they want their models, what are called to be well regularized, which means that the coefficients of the models themselves, they don't want to be too big. And we'll get to this in a bit. And so, in fact, what this kind of statement is saying, if I let x naught be 0, if I start my algorithm at the origin, this is going to be my statistical model, okay? My statistical model can't get too big if I can control k. So I could just sort of say, I don't want the coefficients of the model to be more than 500. Okay, so run this for 500 squared iterations, and I'm going to be fine, assuming this number here is, say, 1. Okay? All right. So that was steepest, that was greedy coordinate descent. There's also gradient descent. So the gradient descent algorithm it's a little easier to state. It just sort of says, start at a point, okay? At each iteration, compute the gradient, choose a step size, alpha hat, and then set the new point to be the old point minus the step size times the gradient. Right? That's regular, what's called L2 steepest descent, or just steepest descent often. And there's a picture of it. All right? And I'm also going to show you, and there's tons of results for that I'm not going to, similar kinds of results that there are then for greedy coordinate descent. And now, here's another algorithm that this algorithm I find very, very frustrating as an academic. Sergio is laughing here, all right? Because this is the algorithm that is the favorite algorithm in machine learning right now, okay? Machine learners tackle all their deep neural nets, right? All their artificial neural nets or their convolutional neural nets with stochastic gradient descent, okay? And it tends to work reasonably well, and no one knows why, okay? But that this is, as an academic, okay, and as someone who likes to take care in what they do, the success of stochastic gradient descent in practice is almost an embarrassment, okay? And I actually mean that sincerely. I'm not trying to just be cute, okay? And so, but let me just show you what this method is. So watch this. Here's how it works. Start at a point. Don't compute the gradient. Compute an estimate of the gradient stochastically, and I'll show you how we might do that, okay? Choose a step size, and then pretend it's the gradient and just go with the negative of that estimate of the gradient. That's stochastic gradient descent. So simple, it's not even funny, okay? All right. So here's the canonical setting for why stochastic gradient descent is so useful, okay? So these days, when you're like training a giant neural network, okay, you train the neural network by saying, I want to minimize the average losses, okay, for each of my samples. So, you know, how close is this sample, how close is my model to the known observed value of my dependent variable, and this is what's called a loss function. And then this, now think of n as being, say, 10 to the 8th, okay? And so if I wanted to compute the gradient here, I need at least 10 to the 8th computations, all right? So just to add up the gradients from all of the estimates, okay? And so instead of computing the gradient, I'll cheat, okay? Let me pick one of these indices at random, okay? And I'll just assign my stochastic gradient to be the gradient just of that component, okay, just of that piece, all right? Now, that is unbiased in the sense that the expected value, okay, over all of expected value of this stochastic gradient will be the gradient itself, all right? But, and that's going to be very useful, all right? So that's sort of the classic setting in which it's used. So let's make two assumptions, all right? We're going to make, the assumption is, sorry, not assumptions, I should say conditions, okay? The first condition is just that the expected value of my stochastic gradient is the gradient itself, all right? And the second one is that these pieces are not huge, okay? And this sort of says the norm of my stochastic gradient squared in expectation is at most some number g squared, okay? And this is very easy to satisfy, all right? It just means, just think of it as like, okay, all of my gradients, all of my derivatives are bounded. You get that, okay? But we don't even, it's even weaker. It sort of says its expected values are bounded, which is whatever, even weaker. And so if I choose my step sizes, say set all my step sizes to be the same, some alpha bar, then you can show that the expected value of the optimality gap is bounded by this mess over here, okay? And the point I'm taking here actually is going to be the average of all the previous points in the algorithm. So I start here, I compute a stochastic gradient, I go over here, I compute a stochastic gradient, I go over here, I compute a stochastic, right? This is a random process, okay? If I take the average of all of those points, that's x bar k, and it is expected to do very well, all right? And we'll just see an example of that. Or sorry, not seeing an example of it.
Paula y me dejó todo esto para que lo guardara.